My name is Elijah Pelofske, and I am presenting the paper, Reducing Quantum Annealing Biases for Solving the Graph Partitioning Problem. This is joint work with Georg Hahn and Hristo Djidjev. The D-wave quantum annealer minimizes Kubo and Ising problems using quantum annealing. A set of linear weights and quadratic couplers define the particular Ising or Kubo that can be solved by the quantum annealer. An Ising has variable states 1 and -1, whereas a Kubo has variable states 0 and 1. Importantly, NP hard problems can be expressed as an Ising or a Kubo. Kubos and Isings are equivalent, but for this presentation, we will focus on Isings. The first step in solving a problem on the D-wave quantum annealer is to express the problem as an Ising. As an example, consider this very simple Ising involving 3 logical variables. Isings can be expressed as graphs because Isings have 2 different types of terms, linear terms represented by nodes in the graph, and quadratic terms represented by edges in the graph. In our example, we have 3 vertices, 1 for each variable, and then we have 2 quadratic terms, J12 and J23, which are represented by edges. The upper right-hand corner shows a 4-unit cell subset of the D-Wave 2000Q hardware connectivity. The D-Wave 2000Q has a hardware connectivity called a chimera graph. On a complete 2000Q hardware connectivity graph, there are 256 chimera unit cells. Since the D-Wave hardware is not all-to-all connectivity, we must find a minor embedding of our logical problem onto the physical hardware. In this minor embedding process, each logical variable from our Ising gets mapped to a series of physically connected qubits. This series of qubits that represents the logical variable is called a chain. If the problem connectivity does not require chains for additional connections, then a logical variable can be represented as a single qubit, as opposed to a series of connected qubits. In the case of our small example Ising, one possible minor embedding is shown in the right-hand figure, where the red variable has the longest chain. For this example, we assume that this small Ising is part of a larger Ising, which requires this particular embedding. We assign large magnitude negative values to the couplers in the chains with the intent to produce equal values of the qubits in the chain when those chains are read out in the annealing process. This large magnitude value is called chain strength. Due to a variety of sources of noise, the samples we get from the annealing process may have chains whose qubits disagree. We call these broken chains. However, we must find a way to resolve these broken chains to a single variable state. This process of resolving these chains is called unembedding. For our example, the red chain is broken and the green chain is not broken. The chain strength we use to construct the embedded problem is important because if the chain strength is too small, then many chains will be broken. On the other hand, if the chain strength is too large, then the chains may not be broken, but the solution quality will be low. D-wave quantum annealers have a variety of sources of bias and noise, including precision limits because the coefficients are scaled into a hardware specified range and rounded to 8-bit precision. There are also variations in the hardware manufacturing process, as well as defects in some of the qubits and couplers, and variations in the calibration procedures for the device. The choice of the minor embedding we use for a problem also affects how the problem is solved, especially because the chains representing the logical variables have different lengths. Because quantum annealers in part use a quantum state in order to carry out computations, Any noise, such as thermal noise from the environment, will degrade the quantum state of the qubits. And completely isolating a system from environmental noise is very difficult to do. Lastly, coupler leakage can cause couplers to modify the intended state of its incident qubits. All of these biases and sources of noise cause D-Wave to be a biased sampler. For modern quantum annealing technology, noise and bias is probably the most serious problem. The objective of this work is to mitigate the effect of various sources of noise on the D-Wave quantum annealer. We apply our methods to the NP-hard problem, graph partitioning. Graph partitioning is an NP-hard problem where the task is to divide the vertices of a graph into two disjoint and balanced sets, such that the number of edges connecting those two sets is minimized. This problem statement has two parts: the constraint of a balanced set of vertices and the objective of minimizing the number of edges, i.e. the cut size, between two sets. Graph partitioning is a useful problem to solve for real-world applications. One example is load balancing in high-performance computing. Equation 2 shows us the Ising model for graph partitioning. We can see the two components of the Ising model are the balance constraint and the objective function. The balance constraint is minimized when the two sets are balanced, i.e. they differ by at most one node. And the objective is minimized when the cut size between the two sets is minimized. The resulting variable assignments we get for each graph node tell us which of the two partitions the node falls into. We choose the coefficients a and b such that a over b must be greater than or equal to n over 8, where n is the number of nodes in the problem graph. The general idea for our bias correction algorithm is to consider the effect of the biases on the constraint and the objective separately. The first step is to quantify the biases on the quantum annealer when we only solve the constraint, not the constraint plus the objective. Then we use an iterative algorithm to reduce the biases on the constraint problem. Once we have a debiased constraint, we then add back in the objective function. Finally, we solve the fully debiased problem on D-Wave. When we solve the constraint by itself, we expect to see two different types of biases. The first is linear bias. If there is no objective present, we would expect the assignment of variables to be 1 half the time and -1 the other half of the time. Thus, we define the linear bias measure for a variable as the proportion of anneals which assign the variable state to be -1 out of n anneals minus 0.5. We would expect this measure to approach 0 as the number of anneals goes to infinity if we had a truly random sampler. The second is quadratic bias. Similarly to linear bias, if no objective is present, we would expect the proportion of samples where the variables xi and xj are in the same partition, i.e. they are both -1 or 1, to be 0.5. Thus, the quadratic bias measure for a variable pair, xi and xj, is the proportion of anneals where xi and xj are in the same partition, minus 0.5. Similarly to the linear bias measure, we would expect this measure to approach 0 as the number of anneals goes to infinity if we had a truly random sampler. In our bias correction procedure, we will specifically minimize the quadratic bias, but we will still quantify the linear bias. The iterative algorithm works by correcting the graph partitioning constraints. Those constraints are enforcing balanced sets in the samples we get. If a pair of variables, xi and xj, appear in the same partition very often, then increasing the quadratic weight, j sub ij, will penalize those two variables sharing the same partition, thus correcting that bias. And If a pair of variables do not appear in the same partition very often, then decreasing the quadratic weight, j sub ij, will incentivize both variables to take the same value, thus correcting that bias. Therefore, the update rule we use for a pair of variables I and j is the sum of the previous quadratic weight plus the quadratic bias measure for that edge times a reasonable scaling factor k. This update rule therefore corrects the bias for a particular edge, and the amount we corrected is proportional to how biased the edge was to begin with. Additionally, we do not want to overcorrect by changing edge weights which are not actually biased. Because D-Wave is a probabilistic sampler, one would expect the bias across all edges to be non-zero. Therefore, we only apply the update rule if the bias is more than the threshold parameter tau. This is the pseudocode for the iterative bias correction algorithm. The inputs to the algorithm are the Ising constraint we want to debias, the noise threshold parameter tau, the scaling constant k, and the termination threshold sigma. The termination threshold sigma works by stopping the algorithm if the most extreme biases fit inside the bound of plus or minus sigma. This is our workflow diagram. We aim to correct the graph partitioning Ising given at the top. We do that by applying our algorithm to the constraint only, and after running the algorithm, we obtain a debiased constraint denoted by function c. We then add the debiased constraint to the original objective. In the experimental section, we will show that the D-Wave solutions for the constraint have considerable bias. We will then show that our algorithm corrects that bias, and then we will show how that corrected bias improves the solution quality for graph partitioning problems. For the experimental setup, we will solve random graphs of size 65 and random density between 0.05 and 0.95. The reason for using 65 nodes is because a 65 node complete graph is the largest complete graph we can embed on the Los Alamos National Laboratory's D-Wave 2000Q. We also fix the annealing time to be 1 microsecond. We also determine the chain strength using the uniform torque compensation function, which is part of the D-Wave Ocean SDK. And for the bias correction algorithm, we set our threshold for correction parameter tau to be 0.05, and we set our threshold parameter sigma to be 0.2. Here we see the quadratic bias on the left and linear bias on the right. The closer a distribution is to being centered around 0 in these plots, the less biased that distribution is. The total number of linear biases is 65 because there are 65 graph nodes. And the total number of quadratic biases is 2080 because we get 1 bias measure for each edge in the complete 65 node graph. The red distribution is before correction, and the blue distribution is after the bias correction procedure. We see that the initial biases, shown in red, for both linear and quadratic measures are very clearly substantial. We also see that although we do not specifically correct the linear biases, through correcting the quadratic biases, the linear bias decreases after the correction procedure. In these plots, we observe the progression of quadratic biases as a function of iteration on the left, and the progression of quadratic weights on all edges as a function of iteration on the right. On the left-hand figure, we observe that our bias correction algorithm quickly reduces the sum of the overall quadratic bias Q and stabilizes to roughly 5% per pair. Once again, because D-Wave is a probabilistic sampler, we would expect the algorithm to converge to a non-zero error rate, and we observe this to be the case in the data. On the right-hand side figure, we plot the quadratic weight as a function of iteration for each of the 2080 edges in the 65-node complete graph. By observing the quadratic weights as a function of iteration, we see that some edges cannot be fully corrected, but most edges can be corrected and converge to a consistent quadratic weight. Now we validate how well the corrected constraint works when we add back in the objective information. We perform 10,000 anneals on 1,000 random problems, and we record the best valid solution from both the original Ising and then the bias corrected Ising. Here, the x-axis is the difference in cut size between the original Ising and the bias corrected Ising. This means that the more right shifted this distribution is, the better our method works on average. And a rightward shift is indeed what we observe in this histogram, meaning that the debiased Ising improves on the original average cut value of 496. We showed three important things. One, D-Wave is a biased sampler. Two, we can use an iterative algorithm to correct these biases. And finally, that the bias-corrected graph partitioning Ising yields better results on average than the uncorrected Ising. Future research avenues include linear bias correction, extending our approach to other problems besides graph partitioning, and understanding how the embedding affects the observed bias. Lastly, we could also look at other ways to correct bias on quantum annealers, for example, by using anneal offsets or spin reversals. And that is all. Thank you for your time and your attention.